Okay, this is part 2 of the lectures on equilibrium. Specifically in this video, we'll take a look at 2 examples. What you will usually find with these introductory examples in equilibrium is that they're usually pretty simple and straightforward, but there are some subtleties associated with them, and also they can be algebraically a little bit messy. So let's go ahead and take a look at the first of 2 examples that we'll look at in this video. Once again, there are subtleties associated with each. Okay, go ahead and copy down the problem into your notes. It involves what is called a hinged beam. A hinged beam is common, for example, when you hang something off the end of it, like we're going to do in this example with a sign of some sort. Okay, so let me read the problem to you. A hinged beam is 2 meters long and has a mass of 25 kilograms. The beam is mounted by a hinge on a vertical wall. The beam is held in a horizontal position by means of a cable attached to the wall and at the far end of the beam at a 30-degree angle. So it looks like this. So right here is the vertical wall, like so. Okay, and then here in red we'll say is our horizontal beam, like this. And then right here, this point is what is called the hinge. Okay, and then we've got a cable attached to the opposite end, like so, holding the beam here in this horizontal position. This angle here, call it theta, that's given to us as 30 degrees. Okay, and then at the opposite end here, we have a sign that's hanging from it like so, like this. So this is typical what you would see with a storefront or something like that. You have a beam coming out outwards like so horizontally, and then something is hanging off the side like so. And then what we're asked to calculate then is if the mass of the sign here is given to us as 10 kilograms, what is the force that the hinge exerts upon the beam, okay? Okay, let me go ahead and name some quantities here. Let's say that the beam itself is M1, that's given to us as 25 kilograms. Okay, and then its length L is given to us as 2 meters. Okay, right here is M2, that's the sign that's hanging off the side. This right here is given to us as 10 kilograms. And then we're asked to calculate the force that the hinge exerts upon the beam. In order to do so, we'll add up all the forces exerted upon the beam and set it equal to 0, and then we'll add up all the torques exerted upon the beam and set it equal to 0. So let's now begin to picture the forces exerted upon the beam. All right, some of those forces are obvious. First of all, of course, we have its own weight. So right here, like so, is M2G. Okay, and then we have 2 cables, so 2 tensions. There's a tension like so, T1. There's a tension like so, T2. Now, before we go any further, pretty obviously T2 here is just equal to the weight of this sign, because if we did look at the forces exerted upon the sign, we would have T2 upwards and its weight M2G downwards, which would just cancel each other out, because once again, everything is just sitting there at rest. So T2, in other words, pretty obviously, is just equal to the weight of the sign, M2G. So let's go ahead and calculate that number before we go any further. Just 10 times 9.8, and that's 98 newtons. Like so. Okay, and then we've got the hinge. The hinge exerts a total amount of force on the beam. How do we picture that force if we don't know its direction? The easiest way to do so is just to break it into components. In other words, whatever it is that the force is that exerts upon the beam due to the hinge, it does have a horizontal component associated with it, F sub h we'll call it, and a vertical component associated with it, F sub v. So what we'll do is we'll set up our expressions and ultimately solve for FH and FV. Once we have those components, then we'll add them together to get the total amount of force, okay? Okay, so let's now go ahead and add up the forces. We've got, first of all, T1 here on an angle, like so. So let's immediately start to picture its components like this, where right here is the angle theta. Okay, so let's go ahead and add up the forces. We'll do so vertically. So vertically I have, let's see, right here, a T1 sine theta, and then plus FV, minus M1G, and then minus T2. Like so. And you can see that we have here a bunch of unknowns, FV and T1. Let's now go ahead and add up the forces here horizontally. Horizontally, we just have FH here canceling out with this component of T1 in the opposite direction. This is T1 cosine theta. So FH equals T1 cosine theta. So I've picked up here another unknown in my expressions. Thus far, I've got 2 equations and 3 unknowns. The three unknowns are T1, FV, and FH. So I obviously need another equation, and this has to do with the torques. So let's calculate the various torques that are exerted upon the beam due to these forces, add it all up and set it equal to 0. Remember, as I've said, however, it doesn't matter what you think of as the axis of rotation, but you want to choose a point about which to calculate the torques such that it makes the math as easy as possible. So therefore, what should I do? Well, I've got a couple of options. For example, I could calculate the torques exerted upon the beam due to this point right here. And when I do, there is no torque then therefore exerted by FV or FH because neither of those forces have a moment arm associated with them. So immediately those torques are equal to 0. Or alternatively, I could go ahead and calculate the torques about this point right here, and then I don't have to worry about T1 and T2 because T1 and T2 won't exert any torque because once again there is no moment arm associated with those forces. So then therefore I'm pretty obviously going to choose one of those 2 points. Let me actually go ahead and choose this point right here as my axis of rotation, and then therefore I don't have to worry about the angle here associated with T1. So once again I'm trying to make things as easy on myself as possible. Okay, at any rate, however, let's go ahead and calculate the torques due to these 3 forces here, where right here is our axis of rotation. So let's take a look at, first of all, M1G. Right here is the moment arm, which is equal to L over 2. All right, so we've got L over 2 like so. Here's M1G. These 2 vectors are at a right angle. And now we'll do R cross F. So when I do, I get a torque vector out of the board. We'll think of that as positive. Like so, and the magnitude of that torque vector is going to be M1G times L over 2. Like so. Okay, now let's go ahead and move to this side of the beam. So right here is a moment arm associated with FH. But notice that the moment arm L is at a 180-degree angle with respect to FH. Therefore, is there a torque due to FH? No, sine of 180 is equal to 0. And then therefore, I only have to worry about FV. So right here is my moment arm. This is the length L, like so. We've got FV upwards in this case, like this. Right there is a right angle between those 2 vectors. So now do R cross F here, and you end up with a torque vector that's into the board, like so. So we'll think of that torque as negative. And then therefore this is going to be minus FV times L, like so. So once again, by choosing specifically this point here as my axis of rotation, notice how easy I'm making the math at this point for my torque equation. Okay, so let's go ahead and add up the torques here, just set it equal to 0. So M1G L over 2 minus FVL is equal to 0. And then at this point we can go ahead and now start to complete the problem. So let's go ahead and solve this expression for FV. So the L's here cancel out like so, and when we solve for FV, this ends up then being M1G over 2, like so. So FV actually ends up just being half the weight of the beam. Okay, so let's go ahead and calculate that number. So let's see, the weight of the beam is 25 times 9.8, and then divide by 2. And this comes out to be 122.5 newtons, 0.5 newtons, like so. Okay, and now that I have that value, let's then actually jump up to here and solve for T1. So we'll do that here on the lower board. So I'm going to go ahead and solve, first of all, for T1 sine theta. We'll move the forces to the other side of the expression. So T2 plus M1G minus FV, like so. Okay, divide by sine theta. So, okay, now let's go ahead and find T1. All right, so T2 from earlier, remember, was 98 newtons. So 98 plus 25 times 9.8, and then minus 122.5. Divide all of that by the sine of 30 degrees, and this comes out to be 441 newtons. Okay, and then lastly, now that I have that value, let's go ahead and find FH. So FH is equal to T1 cosine theta. So multiply this by the cosine of 30 degrees, and this comes out to be about 382 newtons, like so. Notice that I ended up with positive numbers for both FV and FH. This then means that I chose the directions of those components correctly on the diagram above. If I had accidentally pointed one of those components in the incorrect direction, then I would have calculated a negative number, which then reverses the direction to the direction that it should be as I originally drew. Okay, so let's take a look at the components now of FH and FV. So here's FH horizontally like so. We just found that to be 382 newtons. Okay, here's FV like this vertically. We found that earlier to be 122.5 newtons. So then we'll do a little bit of Pythagorean Theorem here to calculate what we'll refer to as F total. So this is the total amount of force that the hinge exerts upon the beam. Okay, so 382 squared plus 122.5 squared, take the square root of all of that, and that works out to be about 401 newtons, give or take. And now let's go ahead and find this angle here. We'll call it phi. It has nothing to do with the angle theta from earlier. So let's do a little bit of inverse tangent. So inverse tangent of 122.5 divided by 382. And that angle turns out to be about 18 degrees or so, give or take. Like so. So once again, a rather simple and straightforward problem, but with a little bit of experience, you're able to very quickly figure out the easiest path towards obtaining the answer. Okay, that's the first of the two examples that we'll look at here in this video. Let me go ahead and erase all of this. Okay, and then let's go ahead and take a look at the second of the two examples. I need to reposition my file. Okay, so in this example, we have a 5-meter long ladder. It has a mass of 12 kilograms, and it leans against a frictionless wall. Okay, this is key to solving the problem. It's a subtlety in the problem. I'll go over that in just a few moments. Okay, the point of contact with the wall is 4 meters above the floor. Find the forces exerted upon the ladder by the floor. So it's similar to the beam problem that we just solved. Okay, here's then how we'll picture it though initially. So here's the floor, here's the wall. Okay, and then right here is a ladder that is doing this, like so. The length of the ladder L is given to us as 5 meters. And then this point of contact here with the upper portion of the ladder and the floor, that distance there is given to us as 4 meters. So this is 4 meters, therefore this right here is 3 meters. I just constructed here a 3, 4, 5 right triangle for simplicity. Okay, now we are going to need this angle here eventually in the problem, call it theta, so let's go ahead and find that. So the inverse tangent of 4/3, inverse tangent of 4/3, and that works out to be about a 53-degree angle. Like so. Okay, and now we take a look at the forces that are exerted upon the ladder. Some of the forces are obvious. We first of all have right here at the halfway point, like so, the weight of the ladder, mg. And then just like in the previous example, this point of contact right here exerts a force on the ladder, which has a horizontal and vertical component. Okay, so right here is a vertical component like so. Right here is a horizontal component like so. And then we've got this point of contact right here with the wall. It specifically says that the wall is frictionless. What that then means is that the wall exerts a force on the ladder only perpendicular to the wall. It's a normal force in this direction, like so. This is key to understanding how to easily solve the problem. Let me demonstrate here by using this stick, and I'm going to go ahead and lean it up against the wall. I'm going to have to tilt my phone to do so. Okay, so bear with me here as I tilt my phone. Like so. Let me go ahead and, oops, sorry. Let me go ahead and tilt it down like so. Okay, you can see all my junk there on the table. Okay, and then I take the stick. I take the stick and I lean it up against the door. Like that, and then we consider the door itself to be frictionless. Okay, now in reality, In reality, the stick itself is not a completely rigid object. It sags a little bit under its own weight. So because it sags a little bit under its own weight, it's kind of almost like it's digging into the door a little bit, such that there is a force of friction exerted upon the top of the stick as it leans against the door. Now that's a little bit difficult to see with just this stick. So let me go ahead and use something like this meter stick here, which is a little bit less rigid, and it's able for me to easily bend it like this. So if I lean this stick up against the wall like so, it sags a little bit under its own weight, and when it sags a little bit under its own weight, it kind of digs into the wall a little bit, such that you end up with a force of friction. That's being completely ignored here in this problem. If we did take it into account, we would end up with another unknown that we wouldn't be able to solve for in our expressions. So then therefore, if you encounter a problem that says a frictionless wall, what it specifically means is that the stick is a perfectly rigid object. This then makes the problem easier to solve. It's a subtlety. Okay, let me go ahead and reposition my phone. Okay, now that we have that subtlety out of the way, the remainder of the example is pretty simple and straightforward. Okay, so let's go ahead and add up the forces now exerted upon the ladder here. So let's add them up, first of all, vertically. Vertically, we have FV like so, just canceling out with mg. And then horizontally, we have this force here that's ultimately just canceling out with the normal force like so. Okay, notice thus far that I have two equations, and I have here then three unknowns. The three unknowns are FV, FH, and the normal force N. So then therefore, these two equations by themselves are not enough to solve the problem. Now we can find FV, however. Let's just go ahead and do that. That's just equal to the weight of the ladder. So let's see, the mass of the ladder was given to us as 12 kilograms. I neglected to write that down earlier. Let me do so here. So 12 times 9.8, and that comes out to be 117.6 newtons. Like so. But now let's go ahead and calculate the torques. So in order to calculate the torques, what I'm going to do is choose this point right here as my axis. Therefore, there is no torque due to FH, nor is there one due to FV, and then therefore I'll be able to end up with an easy expression to work with. Okay, so let's go ahead and take a look at, first of all, this moment arm here, L over 2, 4mg. So here's L over 2 and here's mg. And then be careful, this angle right here, you'll notice is theta plus pi over 2. Like so. And now we'll do R cross F here. We'll end up with a torque vector into the board. We'll think of that as the positive direction. So it's going to be in magnitude mg and then multiplied by L over 2 times the sine of pi over 2 plus theta. Let's go ahead and do a little bit of a trig identity here to simplify this quantity. Just be a little bit careful as we go. So mg L over 2 in brackets here. Sine of the first angle, cosine of the second, and then plus cosine of the first angle times sine of the second. Like so. Simplify the brackets. Cosine of pi over 2 is at 0. Sine of pi over 2 is 1. So what you end up with here is an mgl over 2 times cosine theta. Like so. Okay, and now we've got the normal force here. That is this guy, which is a distance L away from the axis. So right here is the moment arm L. Right here is the normal force N. And then on the diagram above, remember that this angle here was theta. So then therefore this right here is pi minus theta. And now when we calculate this torque as R cross F, we end up with a torque vector here out of the board. So we'll have to make that one negative. So this is going to be minus N L sine of pi minus theta. Sine of pi minus theta is the same thing as the sine of theta as we've seen before. Like so, and I end up with that torque. Let's go ahead and add them up. All right, so I have right here this positive torque. Like so, plus the negative torque. All adds up to 0. And now what we'll do is we'll solve for the normal force N. Okay, so to solve for the normal force N, let's see, the L cosine theta actually cancels from the expression like so. And then therefore N ends up being just half the weight of the ladder. Interestingly enough, like so, that's how it works out. So that's once again the half the weight of the ladder, which is in this case 117.6 divided by 2. Okay, 58.8 newtons. Like so. And then therefore, the horizontal component of the force that the floor exerts upon the ladder is the same value. And then once again, we could do Pythagorean Theorem and inverse tangent to find the total force that the floor exerts upon the ladder and the direction that that force vector points, okay? Okay, there's one more lecture on equilibrium to cover. We'll get to that in the next video.